Next, we're going to look at the concept of a valence electron and how that relates to the properties of our elements. So valence electrons are the electrons in all sublevels with the highest principal energy shell, and we call these valence electrons. The electrons in lower energy levels are called core electrons. So atoms with a similar number of valence electrons tend to behave similarly. For this reason, atoms in the same column or group tend to have similar properties, since every element that is in the same column will have the same number of valence electrons. So for example, the element phosphorus has 3s2 and 3p3. These electrons here are valence electrons because they're in our highest principal energy shell. So these are all valence electrons. Whereas all the rest of these electrons, the 1s, the 2s2, and the 2p6, those are all core electrons. Now, all of the electrons are present, but the main ones we're concerned about when we talk about elemental properties are the valence electrons. The valence electrons are the ones that are most readily available to form bonds and to interact with other elements. And because chemistry is the study of how elements are going to react with other elements, the valence electrons tell us the most about how atoms are going to behave. It is not that the core electrons aren't present and that they are relevant sometimes, but by far the valence electrons are our most important, and that's what we're primarily going to focus on. So, the transition metals, so now what we're going to do is we're going to go through some of the different specific areas and talk about how their properties matter based on their valence electrons. The transition metals are located in the D block of the periodic table, and then you have the inner transition metals, which are located in the F block in the periodic table. Because the D and F sublevels are so close to other sublevels, these atoms sometimes have unusual electron configurations. This is what I was talking about in my last video. So they're not always going to show up as your expected order. So again, I showed this example here like we talked about in the last video. Chromium is going to show up as, well, that shouldn't be neon. Let's fix that. Chromium, you should be argon, not neon. Let's fix you. So this would be argon, 4s1. 3d5, even though you might expect it to be argon, 4s2, 3d4. So just as a note, that should not have said neon, that should say argon. I'm going to have to clear this, though, because there's a little bit more. But just know these are supposed to be argon, not neon. We're not going to go into detail about why. You don't need to memorize those trends. But you should know it's okay for these elements to have slightly different configurations. So the transition metals and the inner transition metals are going to be elements that we do not talk as much about in general chemistry. We'll still use them. We'll definitely have compounds with them at time, but we're going to spend more time on the main group elements. And just to mention that. So let's talk about some of these and how electron configuration is going to relate to elemental properties. So the properties of elements follow a periodic pattern. So elements in the same column have similar properties. This means that the elements in a period show a pattern that repeats. So if you go to period 2, it's going to go family 1, or group 1, group 2, group 3, going left to right. Then you go to period 4, down below it. It's going to do the same idea. So the quantum mechanical model explains this because they have the same number of valence electrons. And the types of orbitals they're going to occupy are also going to be periodic. So for example, we have 3 examples on the right here. One called alkali earth metals, halogens, and noble gases. These are 3 examples of groups that have similar properties. So beryllium has 2 valence s electrons. Magnesium below it, it has 2 valence electrons, but just in n equals 3. Calcium has 2 valence electrons in 4s2. Strontium, 2 valence electrons in 5s. All of these have similar properties because all elements that have 2 valence electrons will have similar properties. Now these halogens, as another example, they all have 7 valence electrons. So 2 s electrons and 5 p electrons in fluorine, chlorine, bromine, iodine, and I don't use AT near as much. Don't remember the name. Let me check. AT. Oh man. AT is not a naturally occurring element, then I did not remember your name. AT is astatine. Or I should say at least it is not a stable naturally occurring element. So astatine. There we go. I don't use that one a whole lot. But it also has 7 valence electrons, so when it does exist, it has similar properties to the ones above. And then the same idea with the noble gases. Those all have 2 s valence electrons and then 6 p valence electrons. Noble gases having the one exception that we show up in the families, which is helium behaves like a noble gas, but it doesn't have any p electrons because there are no 1p. So it is the one family that has an exception. All the others have the same amounts. Okay. So now, let's talk about some of the most important families and what properties we want to know. So we're going to start with noble gases. This is a pretty important one, and my slide has a shadow on it, so you can see them before they come up, but that's okay. So the noble gases, with the exception of helium, have 8 valence electrons, 6 in the p, 2 in the s. They are important because they are especially non-reactive. The reason for this is the noble gases are in a configuration that is especially stable. They don't really want more electrons. They don't want to get rid of any electrons. This is why we use them when we did what we talked about as noble gas configurations. These elements are almost always found on their own in exactly these configurations. They are very rarely present in compounds. And even when they aren't a compound, it's because as a scientist, we were probably interested if, hey, can I make this thing bond to something? And that something is probably fluorine, and we'll learn about why later. But other than some compounds that scientists have created in the lab, you're going to see these elements by themselves. They're incredibly non-reactive. They are like the ideal that some other elements want to aspire to. They're like, I would really like to have 8 valence electrons because that just sounds like one of the most stable things in the world. So many of our elements are going to try to achieve an elemental configuration that matches the noble gases. And that's going to help us figure out why certain atoms react the way they do. So let's talk about some other groups that matter. So the majority of our elements are going to be metallic elements. Like we talked about earlier, that the metals are much more common than the nonmetals. So we have alkali metals. Alkali metals are the very first group of the periodic table and appear in the first column. These have exactly 1 more electron than the noble gas before them. In reactions, they tend to lose this electron so that their configuration matches that of a noble gas. And this also means they tend to form a cation with a +1 charge. This is really helpful for some future chapters where we start doing compounds. So we start introducing some ideas here. The second column on the periodic table is the alkaline earth metals. This is when you have 2 or more electrons in the previous noble gas, and that they tend to lose both of these electrons when they form compounds so that they can get the noble gas notation and tend to form a cation with a +2 charge. Again, this will come up as we start to get towards making compounds in the later chapters. So now we have some more metals. The transition and intertransition elements are located in the D block and the F block for the intertransition elements. These are going to tend to lose electrons from the s orbitals and then the d orbitals to form cations. What you'll notice is we didn't say they specifically lose 1 or 2 electrons. They lose different numbers of electrons. So what do I mean by this? This means you can't just look at a transition element and predict how many it's going to lose. They lose different, that's not supposed to say the words elements, different amounts of electrons. It's not easily predictable of electrons. And I'll put in parentheses, not easily predictable. So this will be related to when we start talking about how they're named. It'll affect that when we get to naming compounds with transition elements. So I can't just look at an element because it's not going to lose every d electron and every s electron. So we have to have some additional information to be able to know how many electrons is it likely to lose when it reacts with other things. So we can't just say how much it's going to lose a certain amount. You then have a few p block metals. Those are located on the p block area to the left of the metalloids. Remember that line we looked at? And so in those chemical reactions, they're also going to lose electrons from the s and p orbitals to form cations. And again, we don't have a set number of they lose always exactly this many. We'll have to look at those to see how many they lose. We'll have to look at specific elements. Whereas the first 2 groups always lost 1 or 2, depending on if they're the first or second column. So that's a lot of metals, and that's a lot of information about them. So let's talk about metalloids and nonmetals. So metalloids are located in the p block in the area right along that jagged line we looked at, that steps of that zigzag. Metalloids can be either like metals or like nonmetals. What this means is that they can both lose electrons or gain electrons. You may notice from these patterns, all the metals we just talked about all tend to react by losing electrons. So when metalloids behave like metals, they lose electrons. On the other hand, if they behave like nonmetals, nonmetals tend to gain electrons. So it's possible for metalloids to either form cations, which are things that have lost electrons, or anions, things that have gained electrons. We then have our nonmetals. The nonmetals are all located in the upper right-hand side of the periodic table, in the area above that jagged line. In chemical reactions, the non-metal elements are going to gain electrons in their p orbitals, and they're going to gain enough electrons to form a noble gas configuration. So you can figure out, based on their position, how many electrons they are likely to gain when working with stuff. And these nonmetals, since they're gaining electrons, are going to form anions. Now, we talked about the noble gases. Those are particularly important. I'm also going to mention the halogens specifically by name because they are so reactive that we use them in a lot of reactions, and you'll see them a lot. Halogens are going to be nonmetals. They have exactly one fewer electron than the next noble gas. In their reactions with metals, the halogens are going to tend to gain an electron to become a noble gas. And in their reaction with nonmetals, they tend to share their electrons with other nonmetals. Each atom is able to get a noble gas configuration. So it depends on whether they're reacting with other nonmetals or with metals, what they tend to do. So you'll notice of the specific groups I named that we need to make sure we know, we have noble gases. Those are the ones that occur at the far right and have exactly 8 valence electrons. We have halogens here. So we've looked at the halogens. Those are the ones that are going to have 7 valence electrons. And they're going to tend to gain exactly 1 when they react with metals. To react, noble gases have 8 valence. Then we also talked about alkali metals and alkali earth metals. And they're both metals. But the difference with these was that the alkali metals had 1 valence and the alkaline earth metals had 2 valence. So those are the 4 big sections we're going to talk about of specific columns. Note that this doesn't mean there aren't other groups, and if you Google them, you can find names, things like the chalcogens, but we're not going to worry about the other namings with these. So this will finish up the specific properties we're going to worry about. What we'll be looking at in our next video is how to figure out what ions different atoms are likely to form and what the electron configuration of those ions tends to be.